Okay, in this video I'm going to continue talking about some of the algebraic rules that we can apply to Boolean functions, and we'll see that this also applies to our propositional logic topic coming up this semester. But for now we're talking about Boolean functions, and we're talking about the Boolean functions of two variables. So we're talking about functions which map 0, 1 squared to the set of binary variables 0, 1. So we can think of this f of p and q, where p is an element of 0, 1, is a Boolean variable essentially. Q is also a Boolean variable, and we think of 0 as being false and 1 as being true in this interpretation. And what I want to show you is, I'll just remind you very quickly that we have P and Q. I'm going to make a truth table here. And because there are two inputs, P and Q, and each can take on a Boolean value, either 0 or 1, that means there are 4 possibilities for the inputs P and Q to some function f. Okay? And we have to define that function for all the possible values of the inputs. And we're going to define the AND function by going P and Q like this. And we're going to define the OR function, P OR Q, using that notation. We also have the negation function, which is really just a function of one variable, but I'll go ahead and add it to this truth table anyway. We can. The AND function, here's something to say to yourself in English. The AND function is only true in the case that both P and Q are true. Okay? So we can draw the 1 for the case where both P and Q are true, and that's the statement P and Q are true. It's false otherwise. And another one you can say to yourself in English is that the OR statement is false only when both P and Q are false. So it's just the opposite, and otherwise it's true. Okay? And not P reverses the pattern on P. Every time P is a 0, it becomes a 1, and every time P is a 1, it becomes a 0. Okay? So that's just a reminder of the definitions of AND, OR, and negation. And now I want to tell you about the rule, a couple of the important rules. In the last video I did De Morgan's rules and double negation. This time I'm going to do associativity and distribution. Okay? So the associative, they're pretty easy. Basically it's a lot like algebra with numbers. When you're adding 3 things together, you don't have to put parentheses around them. So for example, 1 plus 2, if I add those 2 together and then add 3 to that, it doesn't matter the order I do it in. I could do it 1 plus 2 plus 3 and add the 2 and the 3 together first. It doesn't matter what order, and I might as well not even put parentheses on it at all. Same thing happens for both AND and for OR. As long as we've got all ANDs or all ORs in the expression. And what I'm going to do now is I'm going to consider the case of n equals 3, where we have f mapping 0, 1 cubed to 0, 1. Okay, so this is a little bit different case than I had down here. And now we're going to take f as a function of p and q and r, like that. And so we're going to have 3 Boolean variables. Okay, and I'm going to go ahead and just write some algebraic statements without writing it all down in a truth table. And the associative rules are as follows. Number 1, p and q. If I AND them first and then AND it with r, it's the same as P ANDed with Q and R, like this. And you might as well, just as in the algebra case, P and Q and R. You might as well just remove the parentheses. This works only when you have ands throughout. It does not work when you have a mixture of ands and ors. But similarly, it works when you have just ors throughout. If we have P or Q ORed with R, you could do it in the other order. You could OR Q with R first and then OR it with P, and they're all equivalent to the same expression without parentheses. Okay? Okay, so those are the two associative rules. And I hope those are intuitively fairly clear, and we can prove them using truth tables by making a truth table for the left-hand side and another truth table for the right-hand side, and just showing that they're the same. The other one is distributive law. And it's very much like in algebra, where you have multiplication distributing over addition. If you'll remember, x times y plus z is equal to x times y plus x times z. And you're familiar with that from your algebra class. And you know you can go in either direction. If you see the right-hand side here, you'll see a common factor in x, and you will factor out the x to go to the left-hand side. If you see the left-hand side, you know that you can go to the right-hand side by just distributing. Distribute the x. Okay? I think that's just what it's called, what you do. And if you have an x, you might call it the FOIL method if you have two variables instead of just x. So that's the distributive law in the algebra of numbers world. In Boolean functions and logic, it works a little bit differently. Here we have two cases. We have, and this is the case where you're mixing ands and ors together, as opposed to the associative law where we have either all ands or all ors. Here we have P and Q or R. So now we have a mixture of ands and ors. And we're going to see, and you can prove this, that and distributes over or. And that's rule number one. In the same way that I had multiplication distributing over addition, I'm going to write P and P and is the thing that I'm distributing, and I'm going to distribute that, and I'm going to go P and Q, and I'm going to go P and R. Okay, I'm going to go P and Q first, then I'm going to go P and R, and I'm going to separate those two by a great big OR. P and Q, P and R, and I need to put them in parentheses to say that I do those operations first and then separate them by an OR. So it's still sort of Q or R, but it's P on the Q, P and on the Q, and P and on the R, with a big OR in between. The second rule is that, and this rule is the and distributes over or. The other one is just the opposite. Or distributes over and. And we're going to write P or Q and R is equal to P or, and now I'm going to go P or Q and P or R. And separate them by an and. And you notice that when I have the mixtures of ands and ors, I have to keep the parentheses here. I have to put the parentheses here. I have to keep them here. I do have to put them here. I'm not allowed to write P and Q or R without parentheses. It's ambiguous. Okay? And this is the distributive law. And you can use the distributive law and the associative law, the double negative law, and De Morgan's laws all on these types of expressions with P's, Q's, and R's, and literally do algebra in this world. Okay, I'll stop there.